Hello everyone. In this video we look at the hexagonal closed packing type of lattice, which we call as HCP. Now this HCP is the most efficient closed packing in terms of 3D arrangement of particles, just like the cubic closed packing, which is the FCC, face centered cubic structure. So we'll explore it. If you look at an HCP unit cell, this is how the HCP unit cell is going to appear. We will be having the corners of the hexagonal cylinder. Each corner will be occupied by one atom, and at the face center of the hexagonal planes we'll have one each atom, and inside the body we'll be having 3 atoms. So what is the overall arrangement? If you see it, the overall arrangement will be like we'll have totally 12 corners, so to say. So 12 corners, there will be 12 atoms. So there will be 12 atoms at the corners, and 2 atoms at the center of, or we can say at the centers of, hexagonal planes. 2 atoms will be at the centers of the hexagonal planes, and 3 atoms will be in the body. So 3 atoms are going to be in the body of the HCP unit cell. So this is how we'll have the arrangement of the atoms. Now before we find out the packing fraction, we will just try and see what will be the effective number of atoms in the unit cell, because the effective number of atoms will be required for finding out what is the packing fraction. What is the packing fraction value? I mean, we have discussed about it in case of simple cubic, BCC and FCC also. Packing fraction is defined as the volume that is occupied by the spheres or the atoms or particles divided by the total volume of the unit cell. So if you look at the contribution of these atoms towards the unit cell, each atom in the corner, we look at any atom in the corner, this will be shared by 6 unit cells. So any corner, right, we can see in this particular plane, this side will have one more and that side will have one more. So 3 hexagonal cylinders, and 3 will be in the below plane. So totally 6 are going to be sharing the atom at the corner. Means the contribution for a particular unit cell will be 1 by 6. So 12 into 1 by 6 is going to be how much? 2. And the 2 atoms at the centers of the hexagonal planes, because this atom at the center of the hexagonal plane will be shared between only 2 unit cells, this one, and we will be having one more hexagonal cylinder above it. So which means similarly the one over here, right, will be shared between this unit cell and the another one which will be below it. So the contribution will be half. So 2 into half is going to be 1. And the 3 atoms within the body, right, they will belong exclusively only to this particular unit cell. Means 3 into 1 will be 3. So the total effective number of atoms inside the unit cell will be what? 2 plus 1 plus 3. It is going to be 6. So in a HCP, for the entire unit cell, the effective number of atoms in the unit cell is going to be 6. Now we will use this while calculating what is the packing fraction. So let us see how do we find out the packing fraction. Now the diagrammatic representation of an HCP is what we are having here. If you look at let's say for this the edge of the hexagonal base is A. So A represents what? Edge of the hexagonal base, and H is the height of the hexagon, R is the radius of the sphere. So if you see along any edge of the hexagon, the 2 atoms will be touching each other. Means the value of A, the edge length of the hexagon, will be equal to what? 2R. And remember the regular hexagon property, the lines that will connect from center of the hexagon to the corner, they will be having the same length as the edge length. and we'll see that every hexagon, right, we can divide this into, if you have a regular hexagon can be divided into 6 equilateral triangles. So if each of these triangles, the area is root 3 by 4 a square, the total area of the hexagon plane will be what? Root 3 by 4 into a square into 6 it becomes, because there are how many? 1, 2, 3, 4, 5, 6. There will be 6 equilateral triangles that will make up the hexagonal plane. Here the derivation will only confine it to the partial method. The relation between a and r is clearly established. The value of a will be equal to 2r. Okay, and the value of h, this we can derive based upon the method of closing, the closing or arrangement of these particles to form the HCP. So what happens is the 3 atoms over here, they will be closely packed to form a void, and the one above and the one below, right, they will be exactly coming and covering the void. So based upon this geometric relation, we will be able to find that the height of this cylinder will be 4 times root 2 by 3 into r. So this derivation we are not getting into it, how the h result comes. So we just take it as an established value. It comes basically from the method of closing of particles to form HCP and the relation that will come as a result of it. So what we have is a will be equal to 2r and h will be equal to 4 root 2 by 3r. So we are going to use this for this particular derivation. Now the volume of the hexagon or any cylinder for that matter, what will be the volume of any cylinder? The base area multiplied by height. And what is the base area? As we were just saying, base area will be equal to what? You can treat the hexagon like 6 equilateral triangles. 6 into root 3 by 4 into a square. That is the area of the hexagonal plane into h. Means 6 into root 3 by 4 into, in place of a what we can keep 2r square, into h, in place of h what we can keep 4 root 2 by 3r. Now if we want to calculate what is the packing fraction, what will be the packing fraction? Packing fraction will be the volume occupied by the spheres or atoms divided by the total volume. So this is the volume of the the entire unit cell. Now we want to find the volume of the spheres, means as we already calculated, the effective count of atoms for a unit cell will be what? 6. So total volume of the spheres will be 6 into 4 by 3 pi r cube. So the percentage of space occupied by the spheres will be the volume occupied by the spheres, 6 into 4 by 3 pi r cube, divided by the total volume, which is 6 root 3 by 4 into 2r the whole square, means what? 4r square, into 4 root 2 by 3 r. We can see, and we will multiply by 100 to get the percentage. So this r cube and r cube will be cancelled. The root 3 here will be cancelled, and finally what we will be getting is the 6 also will be cancelled, and the 4 over here and 4 over here also will be cancelled. So 4 here will be cancelled. What we will be having totally left out is the 74%. So the overall packing efficiency or packing fraction is going to be how much? 74%. And this will tell us the idea of the packing efficiency in case of HCP will be similar to that of the packing efficiency of the cubic close packing. So both FCC, remember FCC also, what is the packing efficiency we had? We had 74%. So here also what is the packing efficiency we are having? 74%. So this is how we will be looking at the packing efficiency calculation. Okay, and so we are not doing the entire simplification, so you can just do it and check. So what will be the the final simplification? We'll have pi by 3 root 2. So we'll be having pi in the numerator, 3 root 2 into 100. So root 2 will be 1.414, pi will be 3.4. So when we approximate it and then simplify, you will get the answer close to what? 74%. Okay, so this is how we will calculate the packing fraction or packing efficiency of the HCP. And here one thing we are taking it as the result is the value of H. We are not getting the derivation of it. H value will be equal to what? 4 root 2 by 3 R. Okay, so we'll look at some of the examples of the different types of lattice arrangement, especially in case of metals, because we are discussing all this for the metals. How the arrangement of the lattice types will be for ionic substances we'll explore in the next video. But purely talking about the metallic lattices, right? Simple cubic ones are the ones, like they are marked in the blue color squares. Manganese will be forming simple cubic. Face centered cubic, we can see that aluminum forms, calcium forms, strontium forms, cobalt, nickel, copper, rhodium, palladium, silver. So we have a set of metals that will be forming the FCC. BCC, we have majorly our alkali metals. So lithium, sodium, all of them, they'll be forming what? BCC. And we have the metals forming HCP. What are these metals forming HCP? Magnesium, scandium, titanium, yttrium, zirconium, lanthanum, hafnium. So we have metals forming HCP also. So technetium, ruthenium, osmium. So these are the examples of the metals, the ones that will form the simple cubic, the ones that will form the FCC, the ones that will form the BCC, and the ones that will form the HCP. So we don't need to remember these values. This is just to give you an idea that the elements that are available, especially the metals, the S block and the D block, we can look at it in terms of how they will be. Some of them will be forming a simple cubic, how some of them will be forming a BCC or FCC, and how some of them will be forming an HCP kind of an arrangement. So this is about the idea of HCP type of lattice. And the one thing that we need to remember is the HCP will be having the same packing efficiency as that of the FCC. So in the next video we'll look at the packing of particles in terms of the metal atoms to get the three-dimensional lattice types. So how we can get different types of lattice types by the arrangement of the particles. That is something that will give more clarity on how the FCC and how the HCP are going to be having the same packing efficiency. In this we have seen that the final outcome is coming same, but how the final outcome comes as same we will be able to understand when we look at the packing of particles to form the 3D crystals.